Hi, section 13.7 of Young and Freedman's University Physics is about damped oscillations. There's a lot in this section that, frankly, is third semester, actually fourth semester calculus differential equations. So there's some things in this chapter that I think might fit some of the critiques of Young and Freedman, although I'm glad it's there. I mean, I personally am glad to have a vision of advanced physics and advanced math, and certainly you can learn the benefit of the things in this section without knowing that math. And so I'm going to try to reduce this a little bit to the stuff that is more attainable for, say, a second semester physics course. Okay, or very advanced first semester course. So damped oscillations, not to be confused with damned oscillations. Anyway, those are the ones that you have when you're in a car that needs new shock absorbers. So real-world systems always have dissipative forces. That is to say, there is no such thing as a perpetual motion machine. There is no simple harmonic motion that goes on forever because there's always some dissipative forces. So the very bad drawing that you're looking at the bottom of the page, the one in Young and Freedman, is much better. This is an example of damped oscillation because you can see what happens is that the amplitude gets smaller and smaller and smaller until finally the amplitude just kind of goes away. So this is underdamping, as we'll see later on in this video. Underdamping in the sense that it dissipates, somewhat slowly, not all at once, which is critical damping. This is underdamping, where it just kind of slowly fades away. So that's what we're talking about here. And a shock absorber is a good example of intentional damping. So what the shock absorber does is it makes sure that you don't feel like you're going like this when you're riding in the car, but rather the shock absorber absorbs the vibrations from hitting a pothole or those sorts of things. And so that's what we're talking about. We're talking about damping an oscillation. So damping is a decrease in the amplitude of an oscillation due to these sorts, due to dissipative forces. Okay? The simplest case is when a frictional damping force is directly proportional to the velocity of the oscillating body. Okay? So we're going to say that the sum of the forces in this case, so F equals negative kx, when you have a simple harmonic oscillator that doesn't really exist. But with damping, you have this other force, which is BV, which is basically some damping constant B times the velocity that you're moving at, the velocity of the x. Basically, we're going to take the negative kx of the simple harmonic motion, and we're going to subtract this proportional, this damping force proportional to the velocity bv, and subtract it, and that's going to give us the sum of the forces on this whatever it is that's oscillating. Okay. Now, visions of differential equations, visions of fourth semester calculus here. Now, if we take this expression at the bottom of the page and we put it into kind of differential form, don't worry about this. If you haven't really mastered calculus yet, don't be afraid. This is, like I said, fourth semester calculus. So, if we take the sum of the forces equals negative kx minus bv. Well, what is it? So let me rearrange it a little bit, and we have F equals ma, right? So there's acceleration. And we have the x, and we have the velocity. This is basically three different orders of a differential equation. So we have this second order differential there of the x. We have the first order differential of the x, and then we have just the x. Well, this is a kind of problem. Maybe I'll do a video on it at some point. There are other videos. I watched a 4-part series by the Khan Academy on solving a second-order differential equation. But basically, don't freak out here is the solution to this. Solving for x, x equals the amplitude times e to the negative b divided by 2m times t, all of that times the cosine of omega t plus phi, or phi, where you remember phi is the phase angle, where it starts in its fluctuation, and so forth. Now, don't let that freak you out. E is, of course, a constant, 2.71828 to infinity. I think it's a very important mathematical constant. But anyway, so you probably, if you're in a second semester physics course, have not had enough differential equations to be able to come up with this. Don't worry about it. Just take their word for it. And again, this is kind of advanced. This applies, by the way, if the damping force is relatively small. Okay, so now again, Young and Freedman don't give a derivation for this expression. We know that in simple harmonic motion, the angular frequency omega is equal to the square root of k over m. So when the oscillation is being damped, the angular frequency is the square root of k over m minus b squared over 4m squared. Remembering again, m is the mass and b is that damping constant. Critical damping. Critical damping is when the system returns immediately to equilibrium without oscillation. This is kind of what you want in a shock absorber, right? Because you want the damping to be absorbed completely by the shock absorber. So basically, this is when the part under the radical up here is equal to 0. When k over m minus b squared over 4m squared equals 0, that's going to be when you have critical damping and the oscillation stops immediately. And so basically that's when the damping constant is equal to 2 times the square root of k times m. That is critical damping, where you reach equilibrium immediately as the oscillation gets to equilibrium immediately, like in a shock absorber, where it immediately counteracts the pothole, and you hardly even notice sitting in the car that you've had an oscillation with the tires. Okay, overdamping is when k is greater than 2 times the square root of km. In this case, the damping force has not returned to equilibrium. It's overdamped. And so the example they give in the book would be if you hit a bump and then you hit another bump. But so the overdamping mostly took care of the first bump, but it's not reached equilibrium to handle the second bump. And so overdamping is not ideal. Now, don't freak out again. This is beyond what a second semester physics student would be able to handle. But the solution for x in this case, and again, this has to do with differential equations, but the solution for x in overdamping is a constant times e to the negative a times t plus a second constant times e to another a times t, negative a times t. And again, Young and Freedman don't even hardly go into this at all. It's something that you would do in an advanced physics course, not in a first, second, or even probably third semester physics course. Okay, so I mentioned that the initial graph is called underdamping. That's where the system oscillates with a steadily decreasing amplitude, where the damping constant is less than 2 times the square root of k times n. So that's where it's going to go slowly down. So you have critical damping, where it immediately reaches equilibrium. You have underdamping, where it slowly reaches equilibrium. And then you have overdamping, where it doesn't reach equilibrium, but it isn't prepared to handle more oscillation. The more oscillation just creates a bad situation. Okay, the final section of this rather advanced section has to do with loss of energy. It's easy enough to understand the way they derive this. They start with the basic total energy equation, E equals 1/2 mv squared plus 1/2 kx squared. I think that's the equation they start with, and then they basically substitute and derive and take derivatives, and basically, but this is what they end up with, that the change in energy in relation to time is basically going to be negative b, the damping constant, times the velocity squared, and that's going to tell you how the energy is diminishing. This is for damped oscillations again, and this has to do with the damping power. The change in energy, is the work being done, and so this is the damping power, the rate of change of energy. Because it's losing energy because the oscillation is being damped. Well, okay, there's some advanced math in this section. What do you need to know? Well, I suspect if you know this equation for the change of energy per time, that would be helpful. And then I don't think this is necessarily something you need to know a lot about at this point. The 2 times the square root of km might show up in some problems as the angular frequency formula there. I'm not sure that this is a formula that he should be doing a lot of they should be doing a lot of problems on for this level. And so basically the concept of damping, overdamping, underdamping, critical damping, that is something that you should probably know. And so we end this section on damping.